Hello everyone and welcome back. Today we're going to talk about section 4.1, extreme values on a closed interval. So in chapter 4, in general, what we're going to do is use the derivative to help us find extreme values on a function. So extreme values just mean minimums and maximums. This is going to help us ultimately graph a bunch of different functions by finding those important points, the minimums and the maximums of the graph. We'll also be able to answer some real-world problems that ask us, hey, what's the least amount of something or the most of something? Those are minimums and maximums. We're going to start in chapter 4 by the graphing process. So before we actually use the derivative to help us find minimums and maximums, we want to talk about the different types of minimums and maximums that exist on a graph. So this is sort of a review. You talk about this typically in earlier algebra classes, but we're going to spend a little bit of time identifying what it means to be a minimum and a maximum, the difference between an absolute minimum and maximum and a local minimum and maximum, and we of course want to remember what other important points on the graph are, like intercepts. So here we have this graph. You might want to pause and write it down or copy it down. We're going to identify different important points. So if you forgot what some of these things mean, it is listed in red at the bottom of this slide. First, we can talk about intercepts. So looking at this graph, you want to remember what intercepts are. Intercepts are the points where your graph crosses or touches an axis. So it looks like we have two of those here. Point A and point C are both on the x-axis, so they're x-intercepts. A also happens to be a y-intercept because it's on the y-axis. So either way, I'm just listing these points. A and C are both intercepts. Okay, so now on to minimums and maximums. So what we're going to talk about first are absolute minimum and maximums. What absolute extrema are, so extrema is sort of the plural, just an umbrella term that combines minimums and maximums together. Absolute extrema are the highest and lowest finite points on the graph that you can see. So it's literally what's the highest point on the graph that you can see, and what's the lowest point on the graph that you can see. So I emphasize the you can see part because a lot of graphs will go up to infinity or down to negative infinity. We can't see those points, so we wouldn't want to include those. Here, this is a good example. So our absolute minimum is the absolute lowest point on the graph that we can see, and that looks like point B. That's the lowest point that that graph gets, so that's going to be the absolute minimum. Absolute maximum is the absolute highest point that the graph gets that we can see, and it looks like that is point F. That's the highest point on the graph, so that's our absolute maximum. Local extrema are a little bit different, so I often call local extrema the humps of the graph because that's typically how they appear. They're going to be inside of our interval, so they're not going to be the endpoints. So A and F are not going to be local extrema. Local extrema have to be interior, they have to be inside, and they typically are represented by humps on the graph. They can look a little bit different, and we'll see different examples, but in general, that's typically what they are. So on this example here, we have a couple humps. So the low humps, like B and E, those are low humps, often called troughs. So you might have seen that on the slide here. Peaks and troughs. Peaks are like mountain peaks. Troughs are little low humps. So we have a couple troughs at B and E. Those are local minimums. And here are the reason why we call them that. So local means just in an area nearby. So if I'm looking at B, if I just look at a nearby area, it's the lowest point, right? If I look a little bit to the left, a little bit to the right, it's the lowest point in that small area. So locally, it's a minimum. It's the lowest point. It's not necessarily have to be the lowest point on the entire graph. It could be. B also happens to be the lowest point on the entire graph, but locally, to be a local extrema, you just need to be the lowest point or the highest point in a small nearby area. So E, you can also see if I cover up the rest of the graph, it's the lowest point nearby. So B and E are local minima. We can do the same thing for maximum. A local max is going to be a peak, like a mountain peak. So it looks like D is a local maximum. It's a hump on the graph, the highest point in a small nearby area. So D is our only local maximum. Again, you might think, well, what about F? F, even if you cover up something nearby, F is still the highest point in a small area. And that's sort of true, But for local, we need it to be on both sides. Because f is an endpoint, there's nothing for me to compare it to on the right side, only on the left side. And we don't like that for local extrema. We need it to have stuff on both sides. So that's just one example. What we're going to do is we're going to formally define these words, absolute and local extrema, and then we're going to look at some more examples where a little bit stranger things happen, because not everything has to be perfect and beautiful like this one example. So let's get on to the definitions. So here are the definitions of absolute extrema. I do recommend pausing and writing these down. They're a little bit more advanced kind of textbook definitions, but you want to get used to seeing and reading and interpreting those as you move forward in your mathematical careers. So absolute extrema, also called global extrema, so that's just another word for that. Global means all over, what's the highest and lowest points. So here's our definition. We let f be a function with some domain D. We say that f has an absolute maximum value on D at a point C if f of C is greater than or equal to f of x for all x in D. So here's what that means. It means that we're going to have an absolute maximum at a certain point, this is an x value, C, if the y value at that point is greater than or equal to the y value everywhere else in the entire domain. So that's what that means. I'm going to have an absolute maximum at a point if its y value is greater than or equal to every other y value that exists in the entire domain of the function. That's why it's the absolute maximum. Absolute minimum, same concept, but instead we have an absolute minimum value at a point C if f of C is less than or equal to f of x for all x in D. So we'll have an absolute minimum at a point C if the y value there is less than or equal to the y value at every other point in that function's domain. So again, on the slide, you want to make sure you know global and absolute are the same thing. They use those words interchangeably. Also, when we're looking at a picture, the absolute extrema are the absolute highest and lowest finite points on a graph that we can see. So just a quick thing about absolute mins and maximums is the extreme value theorem. So the extreme value theorem says if we have a continuous function on a closed interval from a to b, then that function must attain both an absolute minimum and an absolute maximum on that interval. So it's just sort of nice to know if you have a continuous function, we know what continuous means. There's no breaks, there's no holes, there's no asymptotes. Everything is connected. If you have a closed interval, which means you have a starting point and an ending point, so a to b, then there has to be an absolute maximum and an absolute minimum on that interval. And we can see in this particular example that I drew, there's going to be an absolute minimum at A, that's the lowest point on this graph, and the absolute maximum is at B, that's the highest point on this graph, as long as I'm only looking between A and B. So just a nice fun fact that makes sense. Okay, next up is local mins and maxes. These are, again, formal definitions, like textbook definitions that are good for you to know and get comfortable reading. So let's take a look at the formal definition for local extrema, also known as relative extrema. We start by saying let f be a function with domain D. Then f has a local maximum value at a point C in D if f of C is greater than or equal to f of x for all x in D within some open interval containing C. Okay, so a lot of words there, also some new symbols you probably haven't seen before. Let's go through and kind of pick apart this definition. So f has a local maximum value at a point C in D. So this little symbol is just saying we have some x value that we're calling C in our domain, D. That's going to be a local maximum if the y value at C is greater than or equal to the y value for all x's in the domain as long as those x's are within some open interval containing C. So that means we're really only looking nearby that point. Remember, that's what local means. It's just nearby. It doesn't have to be globally the biggest or highest y value on the entire graph. It just has to be nearby. So that's what that means. Some open interval containing C. We're just looking close by, but on both sides. Local minimums are defined similarly. F has a local minimum value at a point C and D if f of C is less than or equal to f of x for all x and d within some open interval containing C. So I'm looking at the slide now. As a reminder, these typically appear as the humps of the graph, although they can be a little bit different. They can technically be, I call them plateaus, which are flat areas on a graph. And they can also be some jumps as well, which we'll see very soon in an upcoming example. Here are some nice pictures of local maximums and minimums. Also, I will say something about our textbook. Our textbook does consider endpoints as local extrema, but I've mentioned that we do not do that, and this shouldn't cause any issues in terms of doing your homework or anything, but I will say if you read the textbook will tell you that endpoints can be local extrema, but we will not interpret it that way. So local mins and maxes can only be internal points. So what I mean by that, they can't be the end points where a graph begins or ends. It has to be inside points, something inside of the curve, as illustrated by this picture here on the slide. Okay, so what we're going to do is we're going to use this information and still just talk about and identify local mins and maxes because we want to get comfortable doing that. So I have a little handout that you can print. It's available to you, and I'm going to follow along. It has 4 different examples on it, and we're going to talk about the mins and maxes and also how to write them appropriately using correct notation. Okay, so if you need to, go ahead and print that out so you're able to follow along. I am ready to go. All right, let's go ahead and take a look at these different examples and identify the local and absolute extrema. So here we have a graph. We're asked to find our local mins and maxes first. You want to remember that local extrema are typically the humps of the graph. So we have a local minimum. It looks like at this point 4, 4. That's a low point on the graph. It's not the absolute lowest point that the graph gets, but it is a little low hump, a trough, as we often say. So we can answer this in a couple ways, and that's really what's important here. So we can answer it as a point. So we have a local minimum at the point 4, 4. Or sometimes we'll say we have a local minimum of, and we put the y value, so the y value is 4. So you want to emphasize that's the y value at x equals 4. And of course, that's the x value. So I have a local minimum y value of 4 at the place where x equals 4. So 2 different ways to answer. You want to pay attention to the way that the homework asks you to do it. Often it'll kind of, if it wants you to answer it in this second way, you might say, how do I know? A lot of times it'll have the words already written for you, and you just have to kind of fill in these boxes like that. So we'll get some more practice doing that as we go through these examples. So local maximum is next. So we have a local maximum at this high point on the graph here. It's a hump. 3, 6 is a local maximum point. Again, another way to say that is we have a local maximum value of 6, that's the y value, at x equals 3. All right, next up is absolute. So we have absolute minimum. You want to look at the absolute lowest point that your graph gets that you can see. So the absolute lowest point on our graph looks like this point, 0, 1. So you can answer as a point, or again, you can say there's an absolute minimum of 1, that's the y value, at x equals 0. And the absolute maximum here is the absolute highest point on your graph. It looks like the absolute highest point on our graph is 3, 6. So that's going to be our absolute maximum. So there we go. That example was very similar to one that we saw already earlier on. So now we're going to move on to things that are a little bit different, more interesting and exciting. So here is our next example. We have this graph. It's a little bit different because it has arrows on it, which indicate that it goes up forever and also to the left and to the right forever. Well, let's go ahead and see if we can still talk about the mins and maxes. So first up, we have local min. So local mins are the humps of the graph, the little low points on the graph. It looks like we have two of them. So we have a local minimum here. That looks like it's the point -1, 1. There's also a local min here at the point 3, 0. So I'm going to list these as points -1, 1 and 3, 0. Again, we can also list them in words. So we could say we have a local minimum of 1 at x equals -1. So that's the first one. And we have a local minimum of 0 at x equals 3. So that's the second one. All right, local max is up next. So also a hump, but it's a little high point on the graph, like a mountain top, a mountain peak. They're often called peaks. So we do have one of those right here at the point 1, 2. That's a local maximum. So we can write it as a point, or we can say we have a local maximum of 2 at x equals 1. Next up is absolute minimum. So that is the absolute lowest point on the graph that you can see. And there is an absolute lowest point on this graph. It's the point 3, 0. So that's the point 3, 0. We could also instead just say there's an absolute minimum of 0 at x equals 3. And lastly, we have absolute maximum. Absolute maximum would be the absolute highest point on the graph that you can see. So looking at this graph goes up and up forever. So there is no absolute highest point on the graph that we can see. There's no boundary. That's kind of what you're getting at. So a lot of people might want to say, wasn't that infinity? Well, infinity is not a boundary. It's more of an idea that just says this graph goes off forever. So there is no absolute maximum. There's no boundary. There's no highest point. The graph goes off forever. So there is no absolute maximum for this graph. Okay, great. So 2 more examples coming up. Again, introducing some sort of weird features. So we're looking at this one here on the left first. And we're going to start with local extrema. So looking at the graph first and foremost, we see a weird feature. There is a jump in the graph, so it's a discontinuous graph, which might cause some issues, but like I said, we'll see. So local minimum. Local minimums typically appear as the humps of the graph. They are small, low points on the graph. So looking at this, there is no low point. There's no trough, a low hump. So there are no local minimums. Next up, local max. So local max is a local high point on the graph. It's typically like a mountain peak. Here, however, it doesn't necessarily look like that, but we do have a local max here. It's going to be at this point, the point 2, 4. The reason for that is because technically it is higher than everything else that's around it. On the left, if I look on the left, yes, it's the highest point. And then as I move to the right, it is a jump, but still everything that's to the right of it is also lower. So it is higher than everything else nearby. So we do have a local maximum at the point 2, 4. And of course, we could also write that as a local maximum of 4 at x equals 2. So local maxes and minimums can sometimes be jumps. I also mentioned a little earlier they can be plateaus too, which are just flat areas on a graph. Okay, absolute min. So absolute min is the absolute lowest point on the graph that we can see. And we do have that. Looks like this point here at 1, 1 is the absolute lowest that that graph gets. I recommend as you're doing this that you always say the definition like I've been doing each time. Absolute min is the absolute lowest point on the graph that I can see. So you want to keep reminding yourself of what that means, and then it'll be easier to answer it. So an absolute minimum of 1, that's the y value, at x equals 1. And then absolute maximum is the absolute highest point on the graph that we can see. And there is an absolute highest point on the graph that we can see. It's this point 2,4. So we can answer it as a point, or we can say there's an absolute maximum of 4 at x equals 2. Okay, and our last example is going to be this one, very unique. So this one has an asymptote, vertical asymptote. It also has some holes in the graph, so that might impact our mins and maxes. Let's take a look. So local min first. Local min is going to be a hump on the graph, a small low point. So it looks like, if I just look at this quickly, like 2, 2, that would be a local min. It's a local low point on the graph, a trough. However, there's a hole in the graph there, which means that my graph does not actually achieve that value. So this is going to be a none answer. We have no local mins. The only one that it could possibly be is 2, 2, but there's a hole in the graph. And I can't have a min or a max if there's a hole, because I don't actually achieve that value. I don't have a point there. So no local mins. Up next are local maximums. So those are also humps of the graph, small high points. So we have this hump here at 4, 3, little mountain peak. It is filled in, so that means we achieve that point, so that's going to be perfect. That's going to be a local maximum for us at the point 4, 3. And we can say that we have a local maximum of 3 at x equals 4. Next up are absolute mins and maxes. So absolute minimum would be the absolute lowest point on the graph that we can see. So you want to notice that this graph points down forever. We have that arrow. So we know the graph goes down and down and down forever. But we can't see that far down. So we're going to have no absolute minimum. There's no restricted lowest point that the graph gets. It just goes down and down forever. So no absolute minimum. All right, up next is absolute maximum. So absolute maximum would be the absolute highest point on the graph that we can see. So you probably would want it to be this point, 1, 4. It looks like it's the highest the graph gets, but we can also see that there is a hole in the graph there. So the graph does not actually achieve that point. I do understand that this graph is not going up to infinity. So you might think, well, there is definitely like a highest point that the graph gets. Maybe there is, but we can't specifically see what that point is. We really want it to be the point 1, 4, but it's not because there's a hole there. If you're saying, well, what about 4, 3? It can't be 4, 3 because we know that the graph does get higher than 4, 3, right? These points here on the graph are higher than the point 4, 3. So the graph does get higher than that. I just can't specifically say how high it gets because the point that I want to say is actually a hole, so I can't say that point. So this one is going to be a none answer. No absolute maximum because I can't clearly see the highest point that this graph achieves. All right, so those are just different examples that we might come across, so it's good to know what local mins and maxes and absolute mins and maxes look like on a graph. I'm going to take a break here, and what we're going to do when we come back in part 2 is we're going to find these mins and maxes algebraically. That means if we don't have a picture of a graph, we just have an equation with x's and y's. How do we find these absolute and local mins and maxes? So very exciting. I'll see you soon in part 2.